All right, so this is going to be the day 15 lecture. Today we're going to be doing our second slideshow over SOLIDWORKS drawings. So this is when you're dimensioning things yourself. This is some slightly more in-depth stuff, but still kind of, the basics. So let's get started here. So just to quickly recap, when we ask you to submit a detail drawing, that means that we're looking for you to submit something that could be manufactured and inspected as you gave it to us. That's going to be a fully done part. For when you hand in your PDFs for this, please you can save your drawing. You know how you click save, you can click save as, and you can save it as a file type. You can just save that file type as PDF. You don't have to print this off and then, scan a PDF of it. You can just print a PDF in SOLIDWORKS. You can just save this drawing file as a PDF, and then hand it in like that. That's just going to be the easiest way. So, little pro tip. Part orientation. This is basically how you put the part on the page. You want to use the minimum number of views, which links to minimizing the amount of hidden lines you have. You want to prioritize the top, front, and right views, the three primary views that we use. Show the essential contours and shapes, and make the best use of space. So if you just have one view on a page, you're going to want to have that view be very large so you can show the details in that. But if you have a bunch of views on a page, maybe you want to shrink them down so dimensions aren't overlapping, that kind of stuff. But the overriding principle to all these rules is clarity. We want to make sure that what you're doing makes sense and is clear. You can break some rules here and there, and if it's on, for the greater good of clarity. So that makes a little more sense as you kind of start doing these a little more. You say, I think I know a better way. And there are many, many ways. I said this to my class, when we first introduced this topic, but there are many ways to do the problem right. There are many ways to dimension something correctly, but there are even more ways to dimension something incorrectly. So that's kind of the two ways you have to think about it. There's a bunch of ways you can do it. There's not just one way. Sometimes you break rules, sometimes you don't. But if it's clear, that's what's important. So, getting started. We did 10 rules last time, so we're going to do another few right now. I can't remember if it's 10 or 8 or what. But basically, place angular dimensions outside the angle. So this one's pretty simple. If you have an angle that you need to measure, the dimension gets put outside the actual angle itself. So those leader lines, those arrows that come, in an arc, they're going to hit, a line that gets drawn by the dimension lines. That one's pretty easy though. For rounded corners, we would dimension them. There are two ways to dimension them. One of them is to give it from the theoretical intersection. What that means is that, you can see on the left here, we have where those two parts would intersect if those lines were to continue. So you have that 72 and 52, and then you have that outside radius. You can also do it, this isn't shown, but what you can also do is if you have a center line, imagine a center line, because these are, imagine this is a pipe. Imagine a center line going through that pipe, through the middle of that pipe. You could measure, similar to how it is on the right, and then measure the radius of the center line. That may not make sense right now, but if that is making sense, then that's good. There are two ways to do it. Just don't dimension from what's happening on the right there, because if you imagine someone needs to inspect that dimension, it would be very difficult to imagine, for example, for that 39 on the top right there, imagining where the part becomes straight. That arc is or that angle's happening, and all of a sudden it becomes tangent with that straight line. Where is that happening? The person inspecting doesn't know, because that's not a real dimension. So something to keep in mind. Dimensioning cylinders. So positive cylinders get dimensioned from the when you see them as a rectangle, or in this case a square, in that view. So basically your distance, your length of it, and your diameter of that circle is going to be in the view that shows it as a rectangle. You do not dimension them in the circular view, which will make sense on this slide, because the holes that are cut in, those holes get dimensioned when you see them as circles, not when you see them as rectangles, because if you were to dimension them, seeing them as rectangles, you'd be dimensioning the hidden lines, right? And we don't do that. So This easily lets you know, just quickly looking at a part, if you see a leader line, that arrow line that goes down to what the dimension is, if you see that line going down to a circle, you know that it's a hole. And if you see it going, in between two things, and you see that diameter, and you see it, going to a rectangle, you know that that's a positive cylinder. So that just helps clear some things up. Avoid crowding. This is a clarity thing. This one's a little easier to understand. But basically, don't have the dimensions all crowded up. Don't put them in places that don't make sense. Avoid crowding, but also avoid having the dimensions that are similar. Because we have here, this is, you could see something like this on the top of, I don't know, a bandsaw or something. Something that has, it's transferring. You want 3 speeds. It's like a bike. It's like a bicycle thing. The gears in a bike. If those things are all, you wanted to measure those diameters going down, you don't want those diameters. You don't want one that's, way up high on the page and one that's way down low, because, that's going to be unclear to someone wanting to see, how the diameters work going down. You don't want them too crowded, but you don't also want them too far apart. You just want them, somewhere in between. So dimensioning holes again. Hole size is best given as diameters with leaders. So we kind of said this in the past, but this is showing you how bad it would be. You can see on the right here, we have that 0.25 from those 4 holes. As you have multiple holes in a part, it starts to get way more unclear about, how those are being dimensioned. So you don't want to dimension them to hidden lines. You want to dimension them as call outs. We have 4 holes that are 0.25 in diameter, and they go through the part. Easy, simple, lets us know quite well what's happening here. So leaders, what we're showing here is that two things that we do and 2 things that we don't do. So on the left here, 2 things that we do. You want a diameter sign, right? And linking to the thing on the right, you want that leader that goes through to not go to the center, right? We want to actually show that the diameter of this circle, which is why the arrow is pointing there, is going to the outside of the circle. And again, on the right, we don't want to use a radius, because sometimes, if you use a radius, then you might use diameter somewhere else, and all your dimensions are going to get screwed up if you get confused between the two. So circles, big circles are, and we'll cover that in a second, but big circles are shown as a diameter, and you attach them to the circle itself. So when you're in the detail drawing in SolidWorks, you click on the circle, and it's going to automatically put that leader out, and you're going to be able to dimension properly. Some cylinder examples. So this is a great example looking at different ways. I think this was on a test last semester. Basically, we show you this part, and we have asked, what's a positive, what's a negative cylinder, how can we identify those? So you can see on the top there, we have the 50 and the 40 on the left and right side, and those we're seeing as rectangles, right? We're looking, we're looking right to the tangent of the edge, and that means that they're going to be positive cylinders. So they're going to be, cylinders that are extruded. And on the bottom, we can see that 30 and the 20, and those are attached to circles, so we know that those are holes. And then you can see them line up with the hidden lines. It all makes sense, and it's very clear. So arcs versus circles. This is very similar to the center line and center mark rule, but basically, if a cylinder is greater than 50%, it's given with a diameter, and that's just the rule right there. So arcs. If it's less than 50. Here are a few ways to do things. So we have the arrow inside and outside here. We show how we attach it to a center line and such like that. Holes, locating holes. So this shows, if we have a positive cylinder, this would be a little different. But basically, with this negative cylinder here, we want to know, if you think about, okay, I need to drill a hole in this block, and how do I know where it's going to go? Well, you're going to say, I'll measure a distance from, the left, and then I'll measure a distance from the top. And then from, knowing those coordinates, then I just need to know how big the hole is going to be, and then I can drill that hole. So it's the same exact way that you dimension it, where basically you give, from left to right, you give a dimension, then from top to bottom, you give a dimension. And then with the leader, you show your how big the hole is. And that's why we have center marks here, so we can show exactly where the center of that hole is. It all makes sense. Whole example with an E below it. I don't know how that happened. basically, so this is for holes that, are consecutive and go around a part. This happens a lot with bolt holes, on a bracket or something, or, there's a ton of times, I'm sure you guys have seen these. But basically, you're going to use an arc or a circle, and a construction arc or a construction circle to show where those holes are. And we do that by having a dimension on that construction arc or circle. So you can see we either have a radius of 66 or a diameter of 110 here. And that shows how far away from the center those holes are going to be. And then you can give, you can say they're equidistant. You can say they have a amount of degrees between them. But there are a bunch of ways to do it. So this is just showing an example. For this arc, though, or for the circle, you need to make a construction circle on the detail drawing, because obviously this isn't going to be here, normally. And so you actually need to go to Sketch and sketch a construction circle on the drawing sheet. And then once this construction circle is set, it's gonna you give a dimension to it. And it's gonna say, do you want this dimension to be driven? And you do want it to be driven, right? Because it's connected to other, hopefully fully defined aspects of the drawing. So that's that. For chamfer dimensions, there is a chamfer dimension tool. If you drop down the smart dimension in your detail drawing, there's a chamfer dimensioning tool, and that'll allow you to give what's happening here. So it's going to require 2 clicks. The first is going to be the edge, so that's the length of 1 there, and then a vertical or horizontal reference, which is the 45 degrees. Let's say, let's look at what this actually means, though, because if we have the same part here, right? Imagine this is the same, it's like just the end piece of a rod. And you see we have 0.4 at 30 degrees and 0.231 at 60 degrees. Those mean different things depending on what edge you're coming off of. And so if it's not 45 degrees, be careful with how you're using the chamfer dimension tool. Maybe it'll be easier to actually give dimensions for it. You want to be able to show exactly what's happening. So keep that in mind when you're using the chamfer dimension tool. That again, it's not always best to use that depending on the situation. So. Symmetry marks. This will save you a lot of time and a lot of room in your drawings. If you have a part that is, big or very symmetric, well, I guess big and very symmetric, you want to use symmetry marks. This is going to allow you to show that, imagine you have this huge bracket and the left and right have the same holes, right? Or those holes are the same size, they're in the same place. You can put symmetry on that part, show that it's symmetric, and then you only have to dimension one of those holes, because we know from the symmetry mark that the other one should have the same dimension. The key, though, is not to overuse symmetry. And to that point, only use symmetry when the part is actually symmetric. Just because some holes are in the same place doesn't mean that the whole piece itself is going to be symmetric. So note symmetry in your drawing here. And for using symmetry marks, make sure, similar to how you don't dimension from hidden lines and stuff like that, don't dimension to the symmetry line. So that's that's part. We can't, similar to how you can't measure from a tangent edge or anything like that, we can't measure from the line of symmetry to a piece. That's not something that we can check on later. And then for symmetry mark placement, it's best to use a leader. If not, you can orient it perfectly so it's it's right in the middle of where that part is. But using the leader is usually, if not always, a better idea. It better shows what's happening. So for adding a symmetry mark, it's pretty easy to do. You just go to annotation, which is going to be on that top bar on the left. You're going to go to geometric tolerance, click that button, and then a window is going to pop up, and it's going to allow you to input a symbol. You click that drop down. There are a ton of symbols you can choose from, but if you're using the symmetry symbol, you're going to find that, click it, and it should populate itself on your page somewhere. If not, just click on your page and one will populate there.